Welcome back to my YouTube channel. If you have been following us up or you are just coming across our video for the first time, do well to subscribe. In this video, we'll be talking about dimension analysis and its application. What is dimension analysis? Dimension analysis is a method used to determine the correctness of an equation. When is an equation said to be valid? An equation is said to be valid if it has equal dimension on both sides of the equation. For instance, let's say we have this equation, force is equal to mass times velocity. To determine the validity of this equation, we need to know if it has equal dimension on both sides of the equation. We know that force has a dimension of mlt minus 2, mass has a dimension of m, and velocity has a dimension of lt minus 1. Simplifying the right hand side of this equation, we have mlt raised to minus 1. As you can see here, both sides of the equation do not have equal dimension, so the equation force is equal to mass times velocity is said to be invalid. Now, let's look at this question. It says, show that the expression P is equal to Fv is dimensionally correct when P represents power, F represents force, and V represents velocity. Here, we are given that power is equal to force times velocity, and we are asked to check for the correctness of this equation. In order to proceed, we need to be familiar with the dimension of these physical quantities. I made a video on how to dimension physical quantities. Do well to check it out. We know that the dimension of power is ml squared t minus 3. The dimension of force is mlt minus 2. And the dimension of velocity is lt minus 1. Simplifying the right hand side of this equation, we have ml squared t minus 3. And as you can see here, the dimension on both sides of this equation are equal. Therefore, this equation can be said to be valid. Dimension analysis is also used in deriving relationships, that is, finding how physical quantities relate. Now, let's take this question. It says, the drag force F on a sphere moving through a fluid depends on velocity v, radius r, and fluid viscosity eta. Derive the relationship F is proportional to v raised to x, r raised to y, eta raised to z. So, we are given F proportional to v raised to s, r raised to y, eta raised to z. Introducing the constant of proportionality k, we have F is equal to k, v raised to x, r raised to y, eta raised to z. We know that the dimension of force is mlt minus 2. The dimension of velocity is lt minus 1. And we know that radius describes a length and the dimension of length is L. Also, we know that the dimension of viscosity is ml minus 1 t minus 1. So now we can write this equation as this. What we simply did here was replace the quantities with their dimension. Next, we remove the brackets by distributing the power outside the bracket to each term inside of the bracket. Doing that, we have this. Simplifying the right hand side of this equation by applying the laws of indices, we have this. So what we simply did here was add the powers of the terms with the same base. Next, we match the dimensions. On the left hand side of the equation, we have m, which is the same as m raised to 1. On the right hand side of the equation, we have m raised to z. For L, On the left hand side of the equation, we have L raised to 1. On the right hand side of the equation, we have L raised to x plus y minus z. For t, on the left hand side of the equation, we have t raised to minus 2, and on the right hand side of the equation, we have t raised to minus x minus z. Equating the power here, we have z equal to 1. Equating the power here, we have minus 2 is equal to minus x minus z. Making x subject of the equation, we have x is equal to minus z plus 2. We know that z is equal to 1. So this becomes minus 1 plus 2. And this gives us 1. Equating the power here, we have 1 is equal to x plus y minus z. Making y subject of the equation, we have y is equal to 1 minus x plus z. We know that x and z are equal to 1, so this becomes 1 minus 1 plus 1, and this gives us 1. So we have x equal to 1, y equal to 1, z equal to 1. Substituting this value into this equation, we have f is equal to kv raised to 1, r raised to 1, eta raised to 1. Now let's look at this question. It says, the speed v of a tsunami wave depends on water depth h and gravity g. Determine the relation v is proportional to h raised to s, g raised to y. Introducing the constant of proportionality k, we have v is equal to k, h raised to x, g raised to y. We know that the dimension of v is lt minus 1. H, which is height, describes a length, and the dimension of length is L. The dimension of gravity is Lt minus 2. Rewriting this equation as this, we have Lt minus 1 is equal to L raised to x times Lt minus 2 raised to y. Removing the brackets, we have Lt minus 1 is equal to L raised to x times L raised to y t minus 2y. Simplifying the right hand side of the equation by applying the laws of indices, we have Lt raised to minus 1 is equal to L raised to x plus y t raised to minus 2y. Matching the dimensions, we have L raised to 1 is equal to L raised to x plus y, and we have t raised to minus 1 is equal to t raised to minus 2y. Equating the base here, we have minus 1 is equal to minus 2y. Making y subject of this equation, we have y is equal to 1 over 2. Equating the base here, we have 1 is equal to x plus y. Making y subject of this equation, we have x is equal to 1 minus y. We calculated y as 1 over 2. Substituting it into this equation, we have x is equal to 1 minus 1 over 2, and that gives us 1 over 2. So we have x equal to 1 over 2 and y equal to 1 over 2. Substituting the value of x and y into this equation, we have v is equal to kh raised to 1 over 2, g raised to 1 over 2, and this is the same thing as v is equal to k square root gh. In summary, dimension analysis is used for checking the validity of an equation, deriving relationship, and also for unit conversions. If you find this video helpful, like, share, drop a comment, and most importantly, don't forget to subscribe.